Hey folks, welcome back to the first video. We're going to do what we can with the rest of the semester. If you have any issues, please don't hesitate to contact me. I'm here to help. If you're having trouble seeing the videos, if you've only got a phone and so the images are really small, just let me know. I can change whatever I'm doing to make it most useful for all of us. So you can see me in this one. I may not always have that video turned on, but yeah, give me a shout if I can help in any way. Our goal here is just to make the best of what we can with what's left of the semester. I don't think this is what any of us would have chosen to be doing right now. So, having said that, our topic that we finished off, well, we almost started, I think, in one section and I started in the other, was this idea of partial fractions. This is the last big section on integration. And so it's really going to be the sort of culmination. The next section, which I'm going to set as kind of homework, is for you to go and look at different integration types, just all mixed up, and work out when and where you should be using each of these techniques. Because so far we've looked at a bunch of different things, right? We've looked at the trig substitutions, we've looked at actual trig integrals, where they're just products of trig functions. This next section is completely new, because we're going to be looking at rational functions. And so by rational functions, I mean functions that are ratios of polynomials. And so here's a couple of examples. Right? They're literally just polynomials, a quotient with polynomials in them. And we're going to use this term proper partial fraction in the same way that we use proper fraction. Right? If I talk about a number like 3/5, that's a proper fraction, whereas 5/3 is not, because the number on top is bigger. So we're taking that same idea over here to polynomials, and we're saying that this is not a proper fraction because the degree of the numerator on the top, this is degree 2, because the largest power on the top is 2. The degree of the denominator is 1, and so it's not a proper fraction because the degree of what's on top is bigger than what's on bottom. This one is proper because on the top we have a 7th degree polynomial, and on the bottom we have a 3rd degree polynomial. Right? And it doesn't matter how I write those. So for example, this is exactly the same integral. I've just reordered the terms. So it doesn't change the fact that this is a 7th degree polynomial because the largest power is 7. I've just changed the order of those 3 terms on the top and the order of the 3 on the bottom. This is still a 3rd degree polynomial on the bottom. So this one is, in fact, again, not a proper fraction because it has a bigger power on top. Now, for example, if we go back to the first one, if I made that a 4 down there, then this is still a rational function. And now I've got a 2nd degree on the top and 4th degree in the denominator. And so because I've got a bigger power down there, now it's a proper fraction. So with that new form, that is a proper partial fraction. So what we want to do is learn how to integrate these things. And we're going to look at a couple of different examples. But before we just do that, I want to remind you of one kind of integral that we've seen before. Let's think about integrating this. The integral of dx over x minus, let's make it 2. How would we go about integrating that? If we're going to use the ideas that we've had before, you can quickly see that this is just a u substitution. Here I'd take u to be x minus 2, and then du and dx are the same because it's just a shift. And when I do that shift, I'm going to end up with the integral of du over u. So you very quickly see that this is the really bad handwriting. This is the natural log of the absolute value of u plus a constant when you integrate it. So in other words, this is the natural log of the absolute value of x minus 2. And we've seen that. We might not have concentrated on it a lot, but we've seen it before. I want you to remember that little calculation. This is the kind of integral we have done before, and more importantly, it's the kind of integral we're going to do a lot. So when you just see literally a shift, in fact, I'll write it down here. Anytime you have an integral that is of the form dx over x minus a, then that integral is going to be the natural log of the absolute value of x minus a. And I'm never going to do a u substitution again. This is a basic integral that we've seen and that we're going to use as we go forward in this section. Okay folks, let's look at this example here. You can see this has a constant term on the top, that's a polynomial, degree 0, and a quadratic on the bottom. So it's a proper partial fraction. And in a similar sense to last time, where we had just a constant on the top, in that case a 1, and a linear term on the bottom, that was a simple partial fraction, sorry, a proper partial fraction as well. So we've got this example, and it really drives everything we do in this section, because our goal here is to factorize. Our goal is to take this expression, factorize the denominator, and then we can use the idea that we had from the previous example. So let's do that. Here's that first here's that term again, but this time I factorize the denominator. It's straightforward to factorize this one, and what I'm going to do now is just some algebra. So I'm going to concentrate entirely on the piece that I'm trying to integrate here, because it's the key. I don't really need to worry about the integral right now. What I'm going to do is use the idea which is key to everything we do in this section, which is I can take this and I can write it as separate linear terms. So the key idea is really to say, suppose that I actually could write this as separate linear terms. In other words, I can write it as something that has the x minus 1 in it and something that has the x plus 2 in it. And we're just doing algebra now, right? So I'm taking each of these terms and I'm writing a single fraction with that as the denominator. Because when I put that back over a common denominator, we do it by multiplying these things together, right? I'm going to take this term, I'm going to multiply it by x plus 2 top and bottom. I'm going to take this one, multiply it by x minus 1 top and bottom, and then I'll end up with this in the denominator. So I'm just going to put a number here because I don't know what that value will be, but I'm just going to hope that it's a number. I'm going to try an A and a B. So these are unknown constants that I'm going to hopefully find. And so then the goal is just to put this back over a common denominator. So I'm going to take that first one and I'm going to multiply it top and bottom by x plus 2. And so that's going to leave us with that term. And then similarly, I'm going to take the second term and multiply it top and bottom by the first one, the x minus 1, which again, the goal here is to give us a common denominator, because then we can combine these terms. Right? Just combining these terms, we've now got A times x plus 2, and then the b times x minus 1 over a common denominator. Right? It feels like we've gone in a complete circle, but let's take that thing and write it back down here. There we go. This is what we've ended up with. We've got on the left 3 over that denominator is equal to some value, and on the right ax plus 2 plus bx minus 1 is equal to that value. And that must be true for all values of x. And so if that's true for all values of x, then I can forget about the denominator because it's the same on the left and the right. So we must have that 3 is equal to that slightly more complicated thing on the top of the right. But again, it must be true for all values of x. And if that's true for all values of x, it must be true for any specific values of x. So I'm going to go on the next page and show you what I mean by that. So we have that expression, and we want it to be true for all x. So we can ignore the denominator. Essentially, we can cancel the denominator on both sides here, right? And we're just left with the numerator. We need this to be true for all values of x. So let's look at some specific values. If it's true for all x, it must be true when x is equal to 1. But when I plug x equals 1 in here, I find 3 is a 1 plus 2 plus b 1 minus 1. And 1 minus 1 is 0. So here a, well in fact 3a is equal to a, so a is equal to 1. So I can find what a must be. And similarly, I can choose a clever value for x to find b, and that clever value to choose is minus 2. What I'm doing is I'm choosing the value of x that makes this 0. So x plus 2 is equal to 0 when x equals minus 2. And the advantage of that is, if this is 0, then I'm just left with this single expression involving b. So when I plug that in, I get 3 is equal to a, x is minus 2, plus 2, those cancel, and we're left with b times minus 2 minus 1. So in this case, we've got minus 3b is equal to 3, and so we can conclude that b is equal to minus 1. Excuse my bad handwriting. So we know what a and b are. So going back to the whole point here is that if we know what a and b are, we can backfeed this into the expression that tells us what this whole thing is. 3 over x minus 1, x plus 2. Well, that's a, which was 1, over x minus 1, plus b, which was minus 1, over x plus 2. And if that's the case, then we can do the integral. Because we can take this whole term and replace it with what we just said, 1 over x minus 1, plus, or we could write it as minus this is the same as 1 over x minus 1 minus 1 over x minus 2, sorry, plus 2. And then I just plug that in, just plug it in there. And with what we found in the previous section, I can immediately, well, not the previous section, but at the beginning today, and we did it in previous sections, I can immediately write down the answer because those two integrals themselves are very straightforward to do. So this is absolute value of x plus 2 plus a constant, and we're done. So it took a lot of work to get there, but the work was all algebra, right? This is all algebra. The algebra is the key here. Once we've got that simplification, once we've written this term, in this original thing in terms of partial fractions, we're good to go. And that thing that we just did is called a partial fraction decomposition. So it turns this rational function into the sum of partial fractions. And what we have then is something we can integrate very, very straightforwardly. This is essentially how half the problems in this section go. We're going to run into another issue, but we'll talk about it in the next video. But let's have another go at one of these. Okay folks, so here is our second problem. You can see it's very similar to the first one, but now we have a linear term in the top, but it's still a proper partial fraction because, how do you spell proper? It's still a proper partial fraction because it's first degree on the top and second degree on the bottom. As long as the denominator has a higher degree, then it's a proper fraction. And these ideas we're talking about will work. So let's go ahead and factorize the denominator, because that's our goal. If we have a proper fraction, that's our first question. So let's turn that into a question. Is it a proper fraction? If it is, then the first thing to do with these problems is to factorize. So let's look at what we get. And again, this is just algebra. So looking at the denominator here, we can see that this thing easily factorizes into x minus 2 and x minus 3. And just using exactly the same idea we took last time, I'm going to take each of those factors and split this into the partial fractions, x minus 2 and x minus 3 in the denominators, with the unknown constants a and b on top. Right? As long as these are distinct partial fractions, as long as these are distinct factors, this is something we're going to look out for. As long as these are distinct factors, we can do this. By distinct, I mean different. This one's x minus 2, this one's x minus 3. They're different. And that means we can split it up in this way. And then we just put it back over the common denominator, right? And I do that literally by multiplying the first one by x minus 3 over x minus 3. And then the second term by x minus 2, top and bottom. And by multiplying those things, we get a common denominator. And then we can combine that all into a single fraction with a common denominator. That's the entire idea of this process. We're just doing algebra, and we end up with the denominator being the original term that we had, the x minus 2, x minus 3, in other words, the x squared minus 5x plus 6. But looking across this, the denominators are the same, but the numerators are different. And the only way that's possibly true is if those two things are also equal. So 2x minus 1 must equal the numerator on the far right there, which is this. I don't know whether you can read that easily. Let's make it yellow or green or something, so maybe it's a bit brighter and easier to read. So this is the expression that we need to satisfy. And this needs to be true for all values of x. And if it's true for all values of x, then it's true for the specific values of x. Well, looking at this, when x is 3, this term disappears. And when x is 2, this term disappears. So I'm going to put x equals 3. And doing that, I get two lots of 3 minus 1 is equal to, well, the first term disappears because it's a times 0. And then the next term is b times 3 minus 2. And so this comes out to be what? 1 lot of b is equal to 5. So there's b. And then using the other value that makes sense to plug in, x equals 2, we can plug in here, this is 2 lots of 2 minus 1, and on the other side we get a times 2 minus 3 plus b times 0, 2 minus 2. So again, that term drops out just like that one did because we made this nice choice for x. And that leaves us with 4 minus 1 is equal to minus a. So a is negative 3. And that is all we need, because that allows us to write down the original integral again. And we simply replace the partial fraction that we had here, the rational function that we had here, with the partial fraction decomposition. That's what we built. We built a partial fraction decomposition. So I'm taking this and I'm replacing it with this. but we've got a specific choice for a and b. Right? This is only true if a happens to be -3 and b is 5. And I could split that up into two separate integrals if I wanted to, because we can just factor the -3 out the front and be left with 1 over x minus 2, and then the dx, or 5 out the front, and then 1 over x minus 3. We can do both of those integrals. This is just like the last one we looked at. Integrating this gives us the natural log of the absolute value of x minus 2, and the -3 out the front. The other one is a 5, and then the natural log of the absolute value of x minus 3, plus a constant. So, the actual integration for these problems is really straightforward. Hopefully you find the integration really straightforward here. The key is to look at this thing, and as long as it's a proper integral, as long as it's a proper fraction, proper rational function, then we can we can factorize and then do this process, which is called breaking it into the partial fractions, right? It's partial fraction decomposition. This process is called partial fraction decomposition, where we take a rational function and we turn it into a bunch of fractions, because we can integrate those fractions. So let's have a look at how these rules come together. Okay, so pulling all those things together, we can see that as long as we have a proper rational function, so we've got to have a rational function, one polynomial divided by another, and it's got to be proper. In other words, the degree of the one on the top is smaller than the degree of the one on the bottom. And it's got distinct linear factors, so it has all of these linear factors, right? I can factorize it. In this case, I'm looking at an nth degree polynomial because there are n different factors here. But as long as I have n different factors, and they're all different, and that's what I mean by distinct, then I can do what we just did. So the first example is exactly of this type. And the fact that I've allowed for an n here means it doesn't matter how many linear factors, as long as they're all different. And so in this case, you can see I've got 3 different linear factors, and in fact, I don't need just a constant up the top, as long as it is smaller than the degree of the polynomial on the bottom. And in this case, there are 3 linear factors, so that's a degree 3. In other words, if I multiply all of those terms together, I'll get a cubic. As long as this is lower degree, and in this case I've made it a square, then we can just use this rule, and we take each of these linear factors, the x minus 3, the x plus 4, and the x minus 10, and we put them in the denominator, and then we put some constants on top. And you can call them a1 and a2 and a3, or you can just call them a, b, and c. So that's the partial fraction decomposition in this case. Something to be aware of, though, is that if you have factors that are not of this form, you should make them of this form first. So in this case, you might want to factor out the 2. So factoring out the 2 will leave us an x minus 2, and factoring out a 2 from the second term leaves 5 halves, right? And so this is 3 halves, putting that half in the top, x minus 2, x minus 5 halves, and then we can do the partial fraction decomposition in this case, just like we did the first one. But I factored out the 2 first, just to make it match the form that we had before. All right, you can do all of the problems that are of this form as long as you have distinct fractions, distinct linear factors like this. So all of the terms in the denominator are different. I'm going to let you start having a go at some of the WebWork problems. I'm going to put a couple of sample problems that you should have a go at immediately on WebWork from the book. And there's also a PDF of the book. If you don't have the book with you, the PDF is available. But yeah, start having a go at these problems. We're going to build on this tomorrow. Thanks for tuning in. Have a great day. Let me know if I can help you in any way. See you later.